Hi guys, in this video I will cover 3 additional alkene reactions. We'll look at oxymercuration, we'll look at hydroboration, and then we'll also look at hydrogenation of alkenes, or hydrogenation. These first two, oxymercuration and hydroboration, we will see that these are 2 additional ways to hydrate an alkene. And hydration of an alkene gives an alcohol, of course. Now we've seen hydration reactions before using just aqueous acid. And we know this involves a carbocation intermediate. And actually this reaction we saw before, this sort of anticipated product is actually the minor product here, and we got a major product due to a carbocation rearrangement. So if carbocations are formed, they can rearrange. What we'll see from these 2 reactions is, well, since they fall under letter B, there is no carbocation intermediate formed in these reactions. Since there's no carbocation intermediate formed here, there are going to be no rearrangements possible. Now what we'll also see is oxymercuration gives sort of the standard alcohol that we would get based on where a carbocation would form, if it actually formed. The hydroboration oxidation sequence gives the atypical alcohol, the other regioisomer, with reverse regiochemistry. Okay. Handout here, oxymercuration. Now if we use water here, it's going to be oxymercuration. If we use an alcohol, it will be called alkoxymercuration. And in either case, it's followed by a reduction step. So that's sort of the terminology. Oxymercuration reduction is the common sort of reaction sequence, and that's shown here with the 1 and 2. Okay, so we can hydrate an alkene with regular aqueous acid. As we showed previously in this handout, that actually gives a rearranged product here, rearranged alcohol. All right. The question can become, what if we wanted this minor product to be a major product? Is there a reaction, a reactant that will give that as the major product? And indeed, the answer is yes. If you use mercury acetate in water in a first step, followed by a reaction with sodium borohydride, NaBH4, we can get that alcohol as the major product. That is, there'll be no rearrangement here because there's no carbocation formed. Let's look at this mechanism. Okay, mercury acetate. We can show this ionic. We can show this, I'm going to show it sort of partially ionized. One acetate and the mercury being positive, and then the other acetate as negative. We can just start there. Of course, you need to know acetate. Yeah? Acetate being that anion there. If there was an H here, it would be acetic acid. And in Gen Chem, you saw things like sodium acetate. All right. Acetate, often abbreviated OAC. We could put a minus there. It could also be 2CH3 minus, or more commonly CH3, sorry, there's a carbon missing there, CH3CO2 minus. That's common there. But this also just equals acetate minus. That's basically OAcyl, because that's an O, and that there is an acyl group. You'll see that over and over, and we'll eventually see it in organic too. So this is an oxygen bonded to an acyl. Oxygen bonded to an acyl. It's really acetyl. Acetyl group, I should say. Acetyl. Okay, so that's acetate. This is mercury acetate. The mercury is 2+. You got 2 acetates minus. We can show it sort of like this. You could show it completely ionic. I'm showing it with 1 acetate still coordinated to the mercury, like this. But here we go. This is mercury plus, just like up here the electrophile would be H plus. H plus in water. Yeah. Here you have mercury plus and water. So the alkene attacks the mercury plus. Where we're going to make cation at? Top or bottom? Would be bottom, so we pull away from bottom and we get bond to mercury. The mercury now becomes neutral because it gained an electron, since it can count one of these in the bond as belonging to mercury. Now, what about this cation? Is it actually formed? And the answer is no, it's not actually formed. What happens next is we have to understand mercury has at least 1 lone pair. Because of that, the lone pair will immediately back bond, and that leads to this intermediate. This is our first intermediate. That's not actually formed. All right, that's just Stevens doing it on the paper. These first 2 steps are concerted. The alkene attacks mercury, but at the same time, the mercury lone pair is back bonding. I'm just showing it 2 separate steps as we've done before. First intermediate. This is called a Mercurinium Ion. Okay? And we can note the similarity of the Mercurinium Ion to the Helonium Ion, like a Bromonium Ion. All right? We saw, like over here, this is the Chloronium Ion, bridged with a chlorine positive. This is a bridged with a mercury positive. Now water attacks. Just like before with the Chloronium Ion, okay, when it strains, would you rather strain and put partial positive on the carbon over here or there? Well, the answer would be this one here, because you'd rather have more positive build up on the more substituted carbon. It can handle more positive charge. Same thing here, more partial plus. See, this mercury pulls here. It back bonded, but it's a weak bond. Would you rather have this one be weak or that one? This one. The weaker this is, the more partial positive on that carbon. If this bond gets so weak that it's not there, then that becomes a full positive on that carbon. Partial plus. Water attacks there, kicks off the mercury. That's going to give the mercury its lone pair back. The mercury is now neutral. Bonded over here. I could draw this up or down. There's no stereochemistry here. I'm going to draw it down because I just have more room. That's the water that bonded. 1 lone pair left, positive charge. A positive species reacts with water, it should be a positive species. Charge is not going to disappear. At this point, something can take the H to go neutral here, the acetate. These electrons take the H, these electrons stay behind, and we're going to get that product plus acetic acid. Neutral, okay, of course is acetyl OH, it's all there. This is in step 1. That's the product that's formed after step 1 here. What have we done to the alkene? We've added an oxygen to it and a mercury. That's why this reaction is called oxymercuration. We just oxymercurated the alkene. Now if we had used an alcohol instead of water, like maybe methanol, we would have an O-methyl here. Because if one's a methyl and the other is an H, you lose the H. And if that's an O-methyl, that would be an alkoxy. It would be an alkyl on an oxy, an alkoxy, and we would have done an alkoxymercuration. So you could also use an alcohol here. Most common is to use water and it just be oxymercuration. Okay, the next step is using sodium borohydride. What does sodium borohydride do? It converts this to that. That's your sodium BH4 minus. Mechanism, we're not going to look at full mechanism. But what needs to take place here? There's 2 H's here, all along, starting with 2 H's on that carbon, 2 H's on that carbon, but now there's 3. The sodium borohydride supplies the extra H there. The mechanism I'm going to show you is probably not the exact mechanism, but let me do it anyway because I think it will be useful, but it's probably not right. First off, sodium borohydride is a source of H minus. Hydride. That's why it's called borohydride. Here's the Lewis structure. The boron has 4 bonds to H. It's indeed a minus charge because boron is only supposed to own 3 electrons. Minus boron, you got to have a sodium or a positive sitting with it. Sodium is most common. Sometimes you'll see potassium borohydride. We can just use this H minus in this mechanism I'm going to show you. What if these electrons just made a bond here and kicked off the mercury? That would indeed give that product. Another H bonded to carbon, that's it. But we would also produce what? Mercury, 1 lone pair, but this arrow gives it another lone pair. Now this would be minus mercury. Because if that's neutral, you're only counting 1 electron for mercury. Now you're counting both electrons for mercury. It's got an extra electron. It's now minus. Well, this thing will break down to mercury plus acetate. And this is actually mercury metal, metallic mercury. Neutral atoms, mercury metal. And that's the fate of the mercury here. And that's bad because it's typically toxic to humans and thus an environmental hazard. because of that, this reaction is not used as much on industry any longer. Not as much as it used to be, 30, 40, 50 years ago. But it's still a very common textbook reaction. Okay, we end up with the standard Markovnikov product. Markovnikov, who was a Russian chemist back in the late 1800s, sort of recognized that you could get standard products, I would call it typical products, and down below it's the non-Markovnikov product. The standard product is the product that you get if the water attack where carbocation would form. That's my terminology, my explanation to you. Where would cation form, top or bottom? Bottom. If water attacks there, you're going to get this alcohol, and thus that's the standard alcohol. Now, if you use this aqueous acid, you actually get this alcohol because of a hydride shift, rearrangement. The important thing about oxymercuration is no rearrangements, because no carbocation has ever formed. That's not actually formed. That's just Stevens showing it on the paper. The first two steps are concerted. The first intermediate is the mercurinium ion. The water then attacks it. You lose proton, you get the oxymercurated product. That you then treat with sodium borohydride in a second step, and it essentially cleaves off the mercury, replaces it with an H, and that's where the new H came from. And you see the new H and the HO there, and so that's H2O added to the original compound. Okay, we'll move on to the next reaction, then we'll try to put some of this in context by working the problems below. Of course, you've got your textbook reading as well. The next reaction, by the way, we also have our outline. Oxymercuration, concerted mechanism involving mercurinium ion. No carbocation, right? Okay, because we said these would be additions without or with no carbocation. Next is hydroboration. Okay, let's look at hydroboration oxidation. Another way to make an alcohol. But this is going to be the so-called atypical alcohol. Where would cation be? Bottom. If water attacked bottom, you'd get OH, oxygen bonded to the bottom. But for some reason, the oxygen is bonded to the other carbon. The carbon where you would not expect carbocation. Atypical product called the non-Markovnikov product, or sometimes called the anti-Markovnikov product. This is BH3. BH3, boron with 3 H's. I'll draw it like this. The boron doesn't have an octet, it's sp2. sp2 with empty p orbital. Okay, if you graphed it, you would see that it has the empty p orbital, 3 sigma bonds to H, no octet. The boron is neutral though. But because it doesn't have an octet, it's electrophilic. That is, electrons are attracted to it. The boron would like to have electrons. The boron wants to take on electrons so it can become more like neon, right? Okay. And the pi bond will attack the boron. Where are we going to leave cation at? Top or bottom? Bottom. Cation on bottom. The boron now still has 3 bonds to H's. Swing out, attack boron, we made that bond. But look at this now, the boron is now minus. And it actually also now looks a lot like sodium borohydride. By the way, we didn't mention why this was an H- source. Because this boron, you can never make boron happy. It either doesn't have an octet and it wants electrons, it's not happy, or it's got an octet but it has too many electrons. At this point, it wants to get rid of electrons. It'll just sort of shoot these H's off and the electrons, and this will go bond to something else. And with H and the electrons with it, that's hydride. And that's what we used here. So this is like darts being supplied by the sodium borohydride. Now the exact mechanism is a little more involved, but I try to keep it simple when we can. And let's just consider it as a hydride source. In organic 2, you'll see lithium aluminum hydride as another hydride source. That's just where the boron's replaced with aluminum, and instead of sodium we have a lithium. But that one's very common and much more reactive. Organic 2. At this point, first off, do you think a cation is formed here? Well, no, because we're under B here, no carbocation. So we know it should not be formed. Why is it not formed? Because as soon as this attacks the boron and the boron becomes negative, guess what the boron shoots at the carbocation? It throws a hydride over there. It's Hydride Shift, okay? Very much like we saw back over here. 1,2 Hydride Shift. All right? Here the H left a carbon and moved to another carbon. Here the H and the electrons leave a boron and move to a carbon. But it's also not 1, 2. If that's 1, that's 2. The boron is 3. So this is actually a 1, 3 hydride shift. And that gives boom, 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 BH2. I'll just show that condensed. That's it. The new H is here. I'm not going to draw it in for you. You need to get used to that. This carbon has 1 H here, 1 H there. But now, and on week 1, you would have told me there's 2 there now. And it's neutral. Where did the extra H come from? It came from the boron. It's a hydride shift. We generated borohydride kind of there. There's your product. This is N step 1. Question. Well, first off, this is, what did we do to the alkene? We added a hydrogen and a boron. We hydroboronated it. We hydroboration. Hydroboration of the alkene. All right. You could isolate that product, but then it's treated with hydrogen peroxide. You've got it written right here, and then hydroxide, such as KOH. And what does that do? Well, it's magic. We're not going to look at mechanism at all. So it's just going to be magic. And what it does is the hydrogen peroxide replaces the BH2, the boron, with what? Replaces it with OH. Okay? Now, you may not want to do this with your notes, but what does it do? Replace this with OH, and there's your product. Simple as that. Mechanism is magic. Now, if you want a detailed mechanism, which hopefully maybe you do want that, you can look online or look in your, maybe in the textbook, but probably online. Importantly, though, replacing the boron, BH2, with OH. Importantly, no change in stereochemistry when applicable. Now this example is not applicable, but later on it will be. And we will say that there's no change. Just do the replacement. So, you see that the OH ends up out on the end because that's where the boron was. And the boron ends up out there because that's how the alkene attacks it. And it attacks it because we know in our mind if we're going to form a cation, we would form it here. Even though we know there's actually no carbocation formed here. And here's a question for you. In the hydroboration, which is the step 1, how many intermediates in the hydroboration of an alkene would be H3? The answer is none. It's only a transition state. It's reacting with the boron. The boron's back bonding. It's not back bonding, it's a shift. You can see how your book describes this. There's no intermediate though. Just a transition state. This is not actually formed in real life. There we go. Here the new thing is replaced with OH. In oxymercuration, the mercury is replaced with an H. And the OH came to the other carbon by reacting. That's where water reacted. So understand the different mechanisms and the different regiochemistry. Okay, products here. Hydroboration, oxidation, anti-Markovnikov product. I'm going to go ahead and draw the product. Let's do that. It's going to be... well, let's do this. We've got a methyl. And the OH is going to be here. How do I know that? Well, anti-Markovnikov. And mechanistically, this attacks BH3. Yeah? Also, the question is, what's the stereochemistry between these two groups? Are they cis or trans? We have a ring here. Let's look at that. This attacks, and it's going to be either forward or back. Let's make it forward. Comes that. That there. But this is not actually formed. What happens next? This throws a hydride here. And that will give now trigonal planar. Now it becomes tetrahedral. Is the methyl forward or back? The methyl group is back. Why? Because the H is forward. And the methyl gets pushed back. Why is the H forward? Simple. Because it came from the boron, which is forward. If the boron is forward, the new H must have come forward. Unless it's going to throw a boomerang hydride. But it doesn't. There's your product. Okay. We will also get the enantiomer. once we start talking about enantiomers. The enantiomer would be where everything is reversed, because instead of this alkene attacking the boron forward, it can also attack it with the boron being back, and everything ends up reversed. At this point, what does the magic do? Hydrogen peroxide and hydroxide replaces the boron. But think about it. This would still be forward. Remember, no change in stereochemistry. And the methyl is back. And is it okay if I don't draw in the new H, as we typically do not? And so the two groups, the two substituents, non-hydrogens, are trans to each other. And so we have both regiochemistry, that is, the OH is going to be bonded to this carbon, this site, not that site. We also have stereochemistry, largely influenced by the fact that the H comes from the boron, and if the boron is forward, the H is going to be forward, pushing the other group back. Of course, you would also get plus enantiomer here. The enantiomer would be where that's bolded and this is dashed. Oxymercuration. Oxymercuration is going to be the Markovnikov product, and that would be that alcohol there, right? Where are you going to make cation at, top or bottom? Top. You can envision water adding. Basically, oxymercuration reduction gives the same product. In fact, H3O plus would work here. Gives the same product as H3O plus does, except it's not going to give any rearrangements. Now, if you use H3O plus here, it wouldn't rearrange anyway, because you'd make a tertiary carbocation, which would be very stable, and then water attack it. What you need to know is oxymercuration gives that same product. It's just not going to give any rearrangements when possible. So again, back over here, I believe we put it in our notes. This would be the oxymercuration product. Which has no carbocation. But if we just use aqueous acid, it would involve a carbocation, because if you would just attack H plus, when you attack H plus or C plus, you're going to have a carbocation. But when you attack a mercury or boron, you do not, because a second concerted step happens at the same time. Okay. And there's no stereochemistry here. We'll learn. There's no chiral carbon. There's nothing to show here. So here's a product from hydroboration. Here, the alcohol from hydroboration, and here's your alcohol from oxymercuration. Okay. Two sort of specialized ways to hydrate an alkene. Both give alcohols, but differences here. Okay, in this handout here, this shows a procedure for actually doing an oxymercuration. This is organic syntheses. You can get this free online. Used to be subscription, but now it's been made free to the public. It shows the exact reaction that we illustrated over there. But it shows you how to some procedural information for those interested. And we see that the OH and the mercury acetate here from the oxymercuration are trans or anti, opposite to each other. By the way, back over here, the BH2 and the H are on the same side, and we call that syn. Okay? So it's a syn addition of the BH3 to the alkene. And that was mentioned in the outline. Syn. The cis means essentially the same thing, but when we do reactions, we typically use anti and syn terminology. And by the way, if you ever see B2H6, it's just a dimer of BH3. If you ever see that, just mark it out and call it BH3. And it's the same reaction, it's just a dimer. That's actually how BH3 exists in solution. Nothing else to worry about there. Okay. You can also see, remember how I said that mercury is formed? It mentions that here. You can find procedures for just about any reaction we ever do in organic syntheses. You can look them up using the index. The other handout here, miscellaneous handout, shows a hydroboration example. And going from 7 to 8, you see we have the alkene here, and you're converting it to the alcohol. And which carbon is the OH going to end up on? By the way, this is not BH3. It's called 9-BBN. It's a BH3 alternative. Anytime you see 9-BBN, just mark it out and show BH3. You're not going to see that from me, but it may be in some textbooks, but I'll never use it. But that's what they're using here. So it's a hydroboration followed by that magic step. Where's the OH going to be? Top or bottom? Or where would the cation be? Bottom. Water adds there, but that's standard reaction outcome. We get the atypical, that means the OH is going to be on the other carbon. Actually the less substituted carbon. And that's indeed how we get product 8. And you can go through that there and think about your mechanism. So this is an example of that type of reaction. By the way, these other handwritten notes, we will see all of these reactions at some point. Between organic 1 and 2. Radical, E2, SN2, those 4 we'll see in organic 1, and these 3 we will see in organic 2. All right, as showed here. So, just trying to show some of the application. This is synthesizing a compound. You can see what they're synthesizing by reading this page. It's good to be familiar with reading research journals. So just giving you a little glimpse of that application. Okay, over here they're doing some research. Basically, it's just another procedure that you can look at, and the sodium there. Just some miscellaneous comments for those who are more interested in the experimental part. which is a very important part of organic chemistry. We just always don't have time to look at it. So these types of things is if you're interested in taking the time. Okay, next reaction. Next reaction is hydrogenation of an alkene. That's shown down here. That would be C, other reaction. Here. Now hydrogenation uses H2. All right. Hydrogen gas, and that's typically going to need to be in a tank. And this shows an apparatus that's common in the lab, in a reaction flask and whatnot. This is called a hydrogenator. Okay, a typical hydrogenation apparatus. We do have one in the department. But again, such is needed for handling gases and getting gases into your reaction and doing it with a closed container. And we also have a shaker here because instead of stirring, it's a motor that shakes the flask. And that's pretty much it. Okay, hydrogenation, one of the most straightforward reactions in organic chemistry, shown here. We're reacting it with H2. And ultimately, we're going to add an H to each carbon of the double bond, the alkene. And when you do that, the alkene becomes an alkane. Now keep track of carbons, 1, 2, 3, 4, 5. Okay, so this is one pentene. And of course, we made pentane. And of course, new H added to each carbon, so this carbon becomes a CH2, and that carbon becomes a CH3. And it's all there. 2 H's have been added. Pi bond is gone. This requires a precious metal catalyst. Catalysts such as palladium, platinum, nickel, or rhodium. Okay, this is ore. One student at one point thought that all of these were required, and so that's why it's ore. One of these, not all of them. Palladium is sort of most common, and then maybe nickel is next most common at the undergraduate level. Research level, palladium is by far the most common. Sometimes platinum. Rhodium would be less common. Okay, mechanism for this. This is showing the atoms of the catalyst. And what happens is the hydrogen gas starts absorbing to the catalyst, the surface. And this is not well known, but it even can start forming to the metal, covalent bonds, and so the hydrogen bond is broken. At this point, the alkene approaches the surface of the catalyst, and then these H's are just sort of shot in like darts to each carbon. All right. Now that's sort of a non-sophisticated description of the mechanism. That's because the mechanism is not well known, and we're not going to use any curved arrows to show a mechanism. The H's are just shot in, and it becomes sigma bonds. And the pi bond is now gone. There's no intermediate here, only a single transition state. The transition state would be H is being shot in, here they come, and bam, product. With just an activation energy, right? But that activation energy is lowered enough to occur by the surface of the metal. If there was no metal here, Hydrogen doesn't react very quickly at all with just a pi bond. But some chemists back in the 1800s found if you include some metals in here that we can get the reaction to take place. Okay. Now, a couple of miscellaneous points here. By the way, it's one of the easiest reactions you'll ever do. Just add an H to each carbon of the alkene. Look at this though. We could also get pentane by reacting to pentene. Of course, either cis or trans. It doesn't matter if the alkene is cis or trans. It's still going to give pentane once two H's are added, one to each carbon. So keep that in mind and see how these both give the same product. Question: which route is more exothermic? A route or B route? Which route to pentane is more exothermic? I'll let you think about that. I would keep in mind we're starting at two different places, but we're ended up at the same place. So determine the energy difference between where you're starting, and then think about which would give off the most energy when the reaction occurs. That's what exothermic means, right? Okay, we also have stereochemistry to consider here. If this cyclohexene was hydrogenated using hydrogen and palladium, and by the way, metals are often dispersed onto charcoal or carbon. It helps spread the metal out and give it more surface area. That's particularly important when the metal is expensive, such as palladium. So if we hydrogenate this alkene, it's important to realize that we would get the cis-only product. The two existing groups, because these carbons are now tetrahedral, the two existing groups will be both forward or both back. Okay? And that would be plus enantiomer. Because that product is chiral, there's no plane of symmetry. We could show them both back. That would also be cis. We would not get trans. Okay? Why do we get cis only? That's because the H's come from the metal. Okay? They come from the same side. Both of these H's were shot in from the same side. We did not shoot one in here and the other one in from the top. That would be opposite or anti. They both come in from the metal. They come in syn addition, same side addition. Okay, we saw that term before with hydroboration. Because they come in from the same side, they're both either going to be forward or back. If they're both back, well, then the other two groups are both pushed forward, and that's why the other two groups are cis. But the two H's could also both be forward. And if they both came in forward, the two existing groups would be pushed back, and they would both be back, but it would still be cis. Okay? Of course, the enantiomer, I'll draw it here. Depending on how much we've looked at that thus far, the enantiomer would be both back. Again, that is cis. Cis, though. This reaction only gives cis. One other comment. It's common in textbooks or courses to use the isotope of hydrogen D2. Sometimes you'll see D2 used. It's the same exact result. The only difference is if you use deuterium, sometimes that allows for additional stereochemistry. And then professors or textbooks can get into more detailed stereochemistry when they use D2. So it allows for deeper thinking about stereochemistry. And we'll see examples at some point. Okay, so that's hydrogenation. Now, hydrogenation is exothermic. We would expect that because we're going from 1 pi bond to 2 sigma bonds. Yeah, you can get your calculator out, but I'm telling you it will be exothermic. Sigma bonds are more stable. Which is more exothermic? You can answer that. We can answer it over here as well. Well, let me go back and answer here because it's more straightforward. Heats of hydrogenation. The least stable alkene will be higher in energy, and it will give off the most heat when hydrogenated. All three of these are hydrogenated to the same place. You need to see that. Draw it to structures. Just depends on what two H's you're adding. You can either add two H's here or there. All right. The heat that's giving off is called the heat of hydrogenation. If we call it a heat of hydrogenation, that would be a positive number. If you call it a delta H, that would be a negative number because it's exothermic. Okay? The more stable compound is going to give off the least amount of heat. That's a lower amount of heat compared to the others that is released. And so this has the lower heat of hydrogenation, and the least stable compound has the highest heat of hydrogenation. Of course, you should know why this is higher in energy compared to that one and that one. I'll let you answer these questions here. One about heat of hydrogenation, but also a couple about some other topics in general, not hydrogenation. Finally, a couple of application pages. This shows a synthesis of the drug Propecia. And going from 43 to 44, we see a hydrogenation. And this double bond right here, this alkene, is being hydrogenated. And there's now two H's here. One of them is drawn in because that carbon is chiral. The other new H is not drawn in. So this is just an example of an alkene hydrogenation, also of course called reduction. Typically when we add H's in organic chemistry, that's called a reduction. One final application is, if you take a look at your steroidal type compounds, testosterone has an alkene, and there's an enzyme that hydrogenates it or reduces the alkene. and it gets reduced to dihydrotestosterone, 2 H's, dihydro. And you see that the one H is drawn in, the other H is here. Now this is a biochemical transformation. Your body does not use H2, okay, or in like palladium. Instead it uses an enzyme. The name of the enzyme is called 5-alpha reductase. And DHT here is important biochemically, both in hair loss in male, like male pattern baldness, because DHT has high activity in the hair follicles, and it can lead to hair loss. DHT is also important in regards to prostate health of men. That's why drugs that inhibit this enzyme can be used to treat hair loss and prostate problems such as BPH. That decreases the activity of DHT, and it improves the condition here. So if we can eliminate or stop this enzyme, we can decrease the amount of DHT produced in the body. Okay, so that is an example of a sort of reduction, an alkene reduction, but it's a biochemical example using an enzyme. Okay guys, that is 3 additional reactions that are important to know. So we looked at oxymercuration, hydroboration, and hydrogenation.